Hi, everyone. It's great to be here in DjangoCon Europe 2021. Um, so my name is Haki Benita. I've been working with Django for a very long time. And I actually do this for a living, working with Django and databases in PostgreSQL and SQL. And I also like to write about it, um, especially about performance and solving problems. And I'm very excited to be here in DjangoCon today and talk to you about performance and indexes and PostgreSQL. So before we start, I want to take a second and talk about this thing called performance. Usually when we talk about performance, we think about speed, but in fact, there's more to performance than just making things faster. So performance to me is what is the best way to balance all the different resources at our disposal. So for example, you have CPU, you have memory, you have disk space, and all of these things cost money. So you also have the cost that you want to optimize for. Now, just as an example, to demonstrate why performance is not always speed, consider, for example, a background process that is doing some work. Now, if this background process takes, I don't know, 1 minute instead of 30 seconds to execute or to complete, it might not affect your application in any meaningful way. However, if this background process consumes a lot of memory or consumes a lot of CPU, it might actually harm the other parts of the system, might affect them. So in this case, you might not want to optimize for speed. You want to optimize for other types of resources such as CPU or memory. So this is something that we are going to talk about throughout this talk. We are not optimizing just for speed. We're optimizing for other things. So who's this talk for? We are talking about indexes in PostgreSQL and Django. So obviously, this is for developers working with Django. But I'm going to talk in different levels. So if you are not even sure what an index is, if you're not working a lot with databases, if you never even explicitly created an index, then this is a great introduction video for you. If you have some experience working with indexes, but you're not sure when to use what type of index and you are curious about it, then this talk is especially for you. And finally, if you're a seasoned developer, you feel comfortable with the PSQL console, you consider yourself an expert in indexing, I think that I can offer some fresh perspectives that might surprise you. So let's start. To come up with different ways of using indexes in Django and Postgres in general, I want to present actual use cases for a real project. So today we're going to work on a URL shortener in Django, and we are going to see different types of solutions and how we can make them better using different types of indexes. So a URL shortener, for those of you who are not familiar with what exactly it does, then a URL shortener takes like a small key that is appended to a usually very short URL. And this short URL can be resolved into a very long URL. This is very useful in platforms that you have a restricted number of digits, like Twitter, for example, or if you're sending SMS messages and you have a limited number of characters that you can use. Another nice feature of URL shorteners is that it provides you some analytics. So a lot of URL shorteners count the number of clicks. So it serves like for analytics. So this is a URL shortener. And if we want to develop a URL shortener in Django, we can create something like this model. So this is a short URL model. We have a primary key, which is a big integer. And we have the key. Key is the last part of the URL which identifies the full URL. We use a char field and we want to keep it short. This is also, it must be unique because this is the identifier that we use to identify the full URL. Then we have the full URL we want to redirect to. We want to keep track of when this short URL was created. So we have a datetime field, and we want to count the number of hits. So every time we redirect, we increment this counter. So just for demonstration purposes, I created this model, generated migrations, applied them, and loaded 1 million short URLs into this table. Okay, so let's start. So the first thing we want to do with a short URL table is to actually resolve a short URL to a full URL. This is what our project actually does. So to do that, we can write this very straightforward function. We call this resolve. The function receives an argument, which is the key, the last part of the URL, and it returns the URL. If the URL does not exist, we get none in return. And if it does, we get the URL to redirect to. Okay? So throughout this talk, we are going to jump between Django and the console and PSQL and PostgreSQL because we want to see what the SQL looks like and what the execution plan looks like. So in this case, if you want to see what the SQL looks like, one way to do that is to turn on this logger in Django settings. Okay, this is very convenient. Once you add this logger, Django will print out the SQL statements that it executes straight in your console. This is very convenient, but just for debug purposes, don't turn this on in production. So if we turn SQL logging on and we execute our function trying to resolve this key into its full URL, we can see that Django constructed an SQL query that fetches all the fields from the short URL table and for a given key. Okay, so this is a straightforward query. This is what you would write if you had to do it yourself. And to see how the database is planning on executing the query, we are going to use explain. Explain is an SQL command that you have in most RDBMSs, and it shows you how the database is planning to actually execute the query. So if we add explain and paste our select statement here, we can see the execution plan that the database came up with. So in this case, we can see that Postgres decided to use an index scan right here using the unique index we have on the key column. Okay, so when we create indexes in Django, by default, Django will create a B-tree index. So the first thing we want to understand is what is a B-tree index? So just like the slide says, B-tree is like the king of all indexes. If you're not sure what you're using a B-tree index. This is the default type of index, and this is most likely what you want like 90% of the cases. We are going to see other types of indexes, but for the time being, we are going to stick with B-tree. So how B-tree works? Let's say we have these values 1 through 9, and we want to index them with a B-tree index. So like the name suggests, a B-tree index is actually a tree structure. And we have the root block. This is the terminology that is used by the database. So this is the root block. And this is how a B-tree works. So everything lower than 3 goes to the left block. Everything between 3 and 7 goes to the middle block. And everything greater than 7 goes to the right block. These low-level blocks are called leaf blocks because they are the leaves of the tree. So to demonstrate how the database is using a B-tree index, let's try to search for the value 5. Okay? So first we start with the root of the index. And we see that 5 is between 3 and 7. So we need to go to the middle block, middle leaf block. This is this block. Now that we have the block, we have the values inside the block, and we scan the values in the block and search for the value that we are looking for. In this case, we are looking for the value 5. The value 5 contains the actual value 5 and a pointer to all the rows that contains the value 5 for this column. So this is how a B-tree index works. So now let's try to see different variations of B-tree index. So going back to the query, when we wanted to resolve this key to the full URL, the database constructed a query, an SQL statement that fetched all the columns from the table for a given key. But if we look at the query, we can see that we don't actually need all the columns. We just want to resolve key to a URL. So we just want this column, right? So the question is, what if we fetch only what we need? Going back to the function resolve, we can change the function that instead of fetching all the fields, we explicitly tell Django that we only want the URL. By providing it with flat true, we can return just the value for the first column, okay? And if it's not found, we return none. If we look at the SQL now, we can see that Django constructed a query that only fetched the URL, which is what we need. If we look at the execution plan, okay, we can see that once again, Postgres used the unique index we have on the key. So that's good. Postgres used the index to find the row and then access the table to fetch the URL from the row, right? This is where a nice feature of Postgres and a nice feature that was added to Django in version 3.2 comes in very handy. This is called inclusive indexes. Some of you may know this as covering indexes, but it's called inclusive indexes. Inclusive indexes lets you include additional values inside the index that are not actually indexed. To do that, we need to switch. Instead of using DB index true or unique true on the field, we need to explicitly create a unique constraint, okay? And if we add this include argument with the name of the field that we want to include in the index, but not actually index, we make this an inclusive index, okay? So if I generate migration, then apply them and run the SQL again, this time the execution plan is a bit different. This time, Postgres used what's called an index-only scan. So this time, Postgres was able to fulfill the query without actually going to the table. And that's because we want to fetch by the key, which is indexed in the index, right? And we want to get just the URL, which we included in the index. So Postgres was able to fulfill the query without accessing the table. You can spot that by looking at the execution plan and searching for index-only scan. Okay, so this is inclusive indexes. And as I mentioned, you might know them as covering indexes. You should know that they can make the index very large, so you need to be careful with it. It's not the worst thing to access the table. And I think that a lot of good candidates for inclusive indexes are usually existing composite indexes, which are indexes that include a lot of columns. So sometimes you can make these indexes better by making them inclusive instead of composite. Okay, so the next scenario you want to implement is try to find unused keys. Unused keys are keys that nobody ever tried to use. So these are short URLs with 0 hits. So we implement this function called find unused keys, and it returns a query set of short URLs with 0 hits. So once again, we want to see what the query looks like. This time we don't need to use the logging because the function returns a Django query set. We can use this attribute called query and print it, and we get the SQL generated by Django. This works because this time we have a query set and not just a string. So once again, Django constructed a query to fetch all the columns where hits equals 0. And if we want to see what the execution plan looks like, we can use this. This is very handy. I think that it was added in Django 3. If I'm not mistaken, this is very handy. So looking at the execution plan, this is how Postgres is planning on actually executing the query. We can see that Postgres is doing a sequential scan on the table. Sequential scan on the table means that Postgres is going to scan the entire table and look for rows with 0 hits. So if we try to optimize that and add a B-tree index on the hits field, We do that by adding a DB index true, generate migrations and apply migrations, and see what the database is doing now. This is with the index. We can see that now the database is using the index we just created on the hits column to find all the rows with 0 hits, okay? So at this point, a lot of very, very good and decent developer would stop and say, that's great, Haki, right? We have a fast execution plan, we have an index and it's being used. But let me remind you, resources and performance is more than just speed. So let's look at the size of the index. So going to PSQL, we can issue a /di plus. I see that the slide is missing the /di plus. Anyway, you'll see that in the next slides. So the size of the index we just created is 7 megabytes, okay? And to try and optimize that, let's consider for a minute, what do we know about unused keys? First of all, most short URLs are used. Just think about it. When someone creates a short URL, it will usually try to test it immediately and it will not be unused. And we don't actually care about short URLs that were used. We only care about the ones where the hits equal 0. So the question is, why even index them in the first place? This is where another very useful feature that I very much encourage you to use, and that's partial indexes. Partial indexes lets you index just a part of the table, which is the part you need. So to use a partial index, we can remove the DB index true from the column and instead explicitly create an index on hits. And by adding a condition, we can make this a partial index. So if we generate and apply migrations and run the execution plan again, we can see that now Postgres is also using the partial index that we just created, but that wasn't the point. Remember, we said that the problem that we've had and the problem that we try to solve is that the index, the full index, was very, very big, right? Was 7 megabytes. So if we look at the size of the partial index, the index that only index short URLs with 0 hits, we can see that the size is now 88 kilobytes. Okay, so that's 99% smaller. So imagine that you don't have 1 million short URLs, you have 1 billion short URLs. This won't be just 88 kilobytes and 7 megabytes. It can be multiplied by hundreds and hundreds. So partial index are very, very useful, and you should use them whenever possible. It can save you a lot of disk space, and as a result, make your queries faster because the database will need to do less I/O. I found nullable columns in, especially in Django, to be good candidates for partial indexes, and I wrote about this here. This is a story of how we save 20 gigabytes of unused indexes just by recreating some indexes as partial indexes. So let's move on to the next use case, the next problem that we are trying to solve. So we want to find short URLs by domain. So we want to find all the short URLs that are targeting a specific domain. Now, let me remind you, we don't have the domain on the table. We have the domain as part of the full URL. So to extract the domain from the URL, we can use custom function in Django that uses a regex to extract the domain part from the URL. Okay, so this is our function get for domain. You give it the domain that you want to search, and it uses a custom function to do it. This is how the query looks like. You can see that Django used the expression and the regex that we generated in the function to query for the domain. And once again, we want to see the explain plan. You can see that Postgres decided to do a full table scan on the short URLs table. And we can also spot that this time the query took a bit more than before. So this time the query took 3 seconds to complete. And that's only on 1 million rows. So This is where another variation of B-tree indexes comes in handy, and that's function-based index, or as I like to call them, FBIs. And using function-based index, you can actually index an expression. So if we take the expression we used in a function before, and we feed that into an actual index, Django index, generate and apply migrations, Django will create an index that indexes this specific expression. So if again, we try to view the explain plan for the query, we can see that this time PostgreSQL was able to use the index on the expression. So we basically used an expression to create an index just on the domain portion of the URL. So we can see that Postgres used the index and the query was much faster. This time it completed in 51 milliseconds, which is 60 times faster than before the full table scan. So function-based indexes are a tricky feature because they are useful if you are using a lot of expressions like the one we just saw. But I personally think that you should avoid them when possible because we can, for example, in this case, when we create a short URL, we can extract the domain and add another field on the short URL with the domain. So now let's look at another interesting use case, and that's reverse lookup. This time we want to search a key by the URL, okay? So far we resolved the key part to the URL, and now we want to do that backward, okay? We want to take a URL that we redirected to and find all the keys that point to it. So we write a function called reverse lookup. It accepts a URL, and it tries to find a short URL, all the short URLs that point to that URL. So once again, we look at the query, and the query is pretty straightforward. Fetch all the fields from the short URL table where the URL is the URL we provided. And we look at the execution plan, and we can see that Postgres is doing a sequential scan, which is a full table scan on the table. It takes 100 milliseconds to complete. Okay. So once again, we can try to add a B-tree index on the URL and see if it can make things faster. Generate migrations, apply migrations, and once again, view the execution plan, and we can see that Postgres is using the index and the query is now much faster, okay? So, are we done? Is that it? Are we finished? Can we go home? I think that we can do better. And if you stuck so far in this talk, you know that we can do better. So if we look at the size of the index, okay? The size of the index on the URL field is 47 megabytes. That's big. That's more than half the size of the table. Okay, so this index will not scale very well. Okay, so what do we know about the URL? We know that URLs are not unique, okay? We can have many keys pointing to the same URL, right? But we know that this is not very likely, so we can assume that URL is almost unique, meaning it's not unique, but it's probably pretty much unique, okay? So this is where a very exotic and interesting type of index, which is not a B-tree index, this is a completely different type of index called hash index, comes in handy, okay? So let's see how hash index work in PostgreSQL. So let's say you have these values in a table, okay? So to construct a hash index, the first thing you need to do is take these values and apply a hash function on them. So Postgres has a lot of hash functions depending on the type. In this case, this is a character, so the hash function is hashchar. Now, I just say you don't need to do anything of any of this. This is something that Postgres does behind the scenes when you create a hash index. So we have the values, and now we have the hash value. Next, we want to divide these values into buckets. So we use modulo the number of buckets. The number of buckets is also something that Postgres determines for you. You don't need to explicitly say how many buckets you want. So in this case, we want 2 buckets. So we divide the values according to their hash values, 2 buckets. So A would be in bucket 1, and B, C, and D would be in the second bucket. And then we can build the index. So this is what basically what the index, the hash index looks like. You might notice that the hash index does not contain the values. It just contains pointers to rows. So if we want to use the hash index and search for the value B, we apply the hash function on the value, get the hash value, and then try to search for the bucket. This time it's bucket 0. So the value B may be in bucket 0, not necessarily, but it's possible that if it's in the index, it's in this bucket. So we fetch the bucket and we scan the rows and we try to search for the value. Okay? So to use a hash index in Django, the first thing you need to know that this is a Postgres specific feature. So you need to import that from country Postgres indexes hash index. So this is how you create an hash index. Previously, we used an index. Now it's a hash index. And we want to index the field URL. Okay? So now, generating migrations, applying migrations, and viewing the execution plan for the query when we have a hash index in place. So the first thing we can see that the hash index was used, right? Postgres did an index scan using the URL HIX, which is the hash index we created. And we can also see that the query was faster. Okay, so the query was faster with the hash index than with the B-tree index. But that's not the point, right? The point was that the B-tree index was 47 megabytes in size, but the hash index is smaller. It's 32 megabytes in size. So that's a 30% savings in size. That's huge. So when hash index is good, is a good type of index. So when the values are almost unique, hash index can be beneficial. One of the benefits of using a hash index is that the hash is not affected by the size of the values that it indexes. Okay, so we use the hash index on URL fields. URLs can be pretty big. Just imagine that the URL can contain query params, hash fragments, encoded strings. It can be a pretty big string. And the B-tree index actually stores the value in the leaves, but the hash index does not. The hash index hashes the values. So a hash index is not affected by the size of the values it indexes. We've already seen that as a result of that, the hash index can actually be smaller than a B-tree, and it can actually be faster than a B-tree. The thing that you need to remember about hash index is that prior to Postgres 10, they were discouraged. They were not production ready, but they are now. So if you are using recent versions of PostgreSQL, you can definitely use a hash index. I wrote a lot about it, hash indexes in this article. You can check it out later. There's a very interesting size comparison that I've done with a B-tree index, but I don't have much time to go over this right now because we have one more index type left. So check out this article if you're interested in hash indexes. Also, I would just mention that hash index has some restrictions because of the way it's built. So you can't use a hash index to enforce unique constraints. You can't have multiple columns in a hash index. And because it does not contain the values, just the hashes, it can be used for sorting and for range searches. But for our use case, it's ideal. So for the last use case that we're going to go over, we want to find all the URLs that were added recently. I see that I'm finished with my 30 minutes, so I'm going to steal like 5 minutes from the Q&A. So the last scenarios we want to try and implement is find URLs that were added recently, okay? So we construct this function. It receives a date and fetches all the short URLs that were created starting at this date, okay? So to use the function, we can construct a date and send it to the function and print the query. So this is what Postgres, this is the SQL that Django constructed, okay? And we want to see the execution plan. So Postgres did scan the entire table, did a full table scan. which makes sense because there's no index. So once again, we can try to add an index on the field. This creates a B-tree index, generate and apply migrations, and once again, get the execution plan. We can see that Postgres used the B-tree index, and the query is now much, much faster, but that's not the point. We are interested in more than just speed, right? So let's check out the size of the index in the database. So using PSQL/DI plus with the name of the index, we can see that the B-tree index on the creation date is 21 megabytes in size, which is roughly 20% the size of the table. So can we do better? Is there some exotic type of index that we haven't talked about yet that can save the day? So you know that there is. You know that there is. So what do we know about the creation date? We know that the creation date is set when the short URL is created. So naturally, it's incremented, okay? So as we add new short URLs, which are appended at the end of the table, the dates of the creation date will naturally be incremented. So one might say that the table is sorted on disk by the creation date. This is actually true for other types of fields like a sequentially generated primary keys, also naturally sorted on disk. So this statistics is actually something very important that the database keeps on your data, and it's called correlation, okay? So when you have indexes with naturally high correlation, columns with naturally high correlation, there's a very special type of index called block range index, or in short, BRIN, that you can use. Now, BRIN is one of my favorite types of indexes because coming from Oracle, I always miss the bitmap index. So how does the BRIN index work? So let's say we have these values in a column, okay? BRIN works by grouping together ranges of adjacent pages. So pages that sit next to each other on the disk are grouped into ranges. So in this case, we are grouping 3 adjacent blocks, okay, 3 adjacent pages. So these are our ranges: 1, 2, 3, 4, 5, 6, and 7, 8, 9. So the BRIN index works by keeping only the minimum and the maximum value in each range. So 1, 3, 4, 6, and 7 through 9. This is the BRIN index. This is what a BRIN index looks like. So if we want to try and search for the value 5 in our table using the BRIN index, we scan the ranges. So the first range is 1 through 3. So the value 5 is definitely not here. The next range is 4 through 6. Now 5 might be here. Note that I'm not saying that it's necessarily here. I'm saying that it might be here. And finally, 7 through 9, 5 is definitely not here. So using the index, we were able to restrict the search just for these blocks, just for these pages, 4 through 6. So instead of scanning 9 blocks, the database can now scan only 3. Okay, so this is how a BRIN index works. Now, remember that we talked about correlation and what happens, and that BRIN index is a good candidate when the values are sorted on disk. So let's see what happens when the values are not sorted on the disk. Let's say that the same values, but this time we shuffle them around, okay? So once again, we create ranges of 3 adjacent blocks and create the BRIN index. So we have 2 through 9, 1 through 7, 3 through 8. And now, once again, we want to search for the value 5. So this time, the index is completely useless because 5 can be in any one of these ranges. So the index is not helping us at all in minimizing the number of blocks that we need to read in order to fulfill the query. Okay? So this is how a BRIN index works. And if we want to create a BRIN index in Django, once again, we go to country Postgres indexes and import the BRIN index. We use it in the index clause of class meta, and we index the creation date, and we give this a name. I'm going to mention this parameter in the end, okay? So generate and apply migration and issue an execution plan, and we can see that Postgres used our index, okay? So this is the BRIN index that we just created. The Key9 reader might see that the execution time is now slightly slower, okay? But that wasn't the point, right? Because we were not trying to necessarily optimize for microseconds optimization. We wanted to solve a problem of a big index. So what is the size of the B tree of the BRIN index? The size of a BRIN index is 248 kilobytes. So just as a reminder, the B tree index was 21 megabytes, and the BRIN index is 99% smaller. So I'm willing to pay this price, like add another millisecond to every query to save so much space. So I'm not going to talk about pages per range because I don't have much time. We can talk about this in the Q&A if you really want to. I'm seeing David like popping up on my screen saying, dude, you need to get off. Okay, I'm going to get
wrap
off.
this up, sorry.
1 minute.
Okay.
So BRIN index is ideal when you have data that is naturally sorted on disk. You can find that with this column in the Postgres information scheme. And this is it. This is like my last slide. So when to use an indexes. Indexes make queries faster, but they also make inserts and updates slower. Okay, and they can also take up a lot of space. So my recommendation to you, bottom line, is just don't overdo it. Okay, just use them wisely. You now know many types of indexes, and you can use them wisely to create an indexes that make things faster but in a reasonable way. So just to wrap up my part of the presentation here, I was Haki Benita. I write a lot about Python, Django, PostgreSQL in my blog. I'm also pretty active on Twitter. You can look me up. And I send stuff to subscriber of my newsletter every month. And if you have any questions, comments, insights, you can do so in the chat, or you can send me an email. This is my email address. So this is it. David, you want to take over?
Yes, and please head to the face-to-face meeting, which you can find in the link below, and ask anything else with you want to know with Haki Benita. We don't have more time. It was a great presentation, and head on to the face-to-face meeting. Thank you all.
And of course, thank you to the organizers of DjangoCon. Wow, a lot of people here. How's everybody doing?
Fine, thank you.
Who am I talking with? I'm new to Jitsi.
Where am I? Yeah, I like to talk. I like there's a topic that we often forget to think about indexes, and we only know it when our app is crashing in production. So.
Okay. Did you find out about a new type of index that you did not know before?
Yes. The inclusive indexes, I was not really aware of them. So yeah, I learned certainly something new. I have one question.
It's probably a good thing that you're not familiar with inclusive indexes. 99% of the time they are used incorrectly.
Okay. Just a question, like in your examples, when you create the indexes in Django, you always provide a name yourself. Can Django also do that automatically for us? Or
if I remember correctly, there are some types of index that you have to provide a name for. So yeah, I think that Django will warn you if you're not adding a name. So don't worry about it. But as a general rule, I think that when you can, you should provide a name, because at the end of the day, you're going to see the index name in execution plans and maybe logs and traces, and you want to be able to identify it. Django is using some hash value, not always recognizable.
All right, thank you.
Cool. Anybody else want to tell me what type of index he likes best? Wow, Jitsi is cool. I never used Jitsi. Anybody is using Oracle here? or everybody is using Postgres?
Hello. Hi, Haki.
Hi.
I have a question about the B tree itself. Can you please briefly explain why B tree is somehow used in Postgres? Because even I think it's a sequential search, or somehow there is more optimization over B tree that Postgres uses. That's why it's a very convenient to use. Can you please explain something about it?
Well, B-tree index, let's go backwards. I think that if you gather like 10 developers in a room and ask them to create an index, I'm pretty sure that most of them will come up with a B-tree index or something that looks like a B-tree index or have a tree structure. So I think that B-tree satisfies the most general cases that most developers encounter. I also think that B-tree index is most of the time the most suitable index for the task. As you've seen with hash index, they have many restrictions, and they're very not ideal for any type of use case. So you have a better chance of getting better performance with a B-tree than any other type of index. This is why I think that presentations like this one that educates developers about different types of indexes and how to squeeze more performance and reduce the size of B-tree indexes is so important.
Okay.
So to answer your question, I think that B-tree is usually the most beneficial, and I think it's most popular because it's the default.
Okay. Yeah. Thank you. One more follow-up question on that. So, because in the slides we have one particular scenario to explain about the performance, but in usually the large applications there could be multiple function call or multiple query execution, right? So on that case, I think using the particular small debugging like the explain won't be sufficient enough. What sort of tools you usually use for that?
Okay, so if I understand the question correctly, you ask what types of tools I'm using to monitor the performance of my SQL.
Yeah.
That's a great question. So in Postgres, I use statement timeout and auto explain to log the execution plans of long running queries.
Okay.
And I also make a habit of setting a timeout for queries that Django executes. Usually it's a very low timeout. This is something that you set at the connection level, or if you're using some connection pool like PG Bouncer. So for me, the default timeout is 10 seconds. So any query that cannot be completed in 10 seconds will be terminated by the database, and I will get an alert. Unless, of course, I explicitly allow the query to execute for more than 10 seconds. I think that this is a good habit to have, along with logging and statement timeout and auto explain. You can have a pretty comprehensive look at the performance of your SQL queries.
Okay. Thank you very much for your answer.
Cool, glad to help. Any other questions about anything? Live.
Hey. So I made a question there on the other platform, but I'll do it here. Again, it's easier. So basically, the last index about the dates, the creation date is basically used for assuming everything is sorted. The question was if there is a way to, after the fact, run some type of script or anything that would force that those dates to actually be sorted, because I had an issue in the past where most of the date would be using the creation date, but some data was synced afterwards by any reasons, and so it was inserted, and the table itself would not be sorted on this mostly, but not everything. And if I wanted to have 100% reliability that I would get all the data, would there be a way to actually sort it, even if it was in another task? Eventually, periodically, and
Yes, there is. There's a command in PostgreSQL called cluster. You can cluster a table according to a specific index. And what the database would do is it will rebuild the entire table in a way that the correlation of the fields that are indexed will be optimized, will be high. Okay, so you have cluster command, which you can use, but you need to be aware that this is a blocking command. So if you run this command on a table, this table would not be available for anything else.
Mm-hmm.
So
And if it's a big table,
with it. There's also PG-Repack and PG-Reorg that you should look into. I usually use PG-Repack to clear out bloat, but maybe you can find a way to cluster the table based on an index using PG-Repack without blocking.
mm-hmm.
Okay?
Yeah, thank you.
That's a good question. Yeah, that's a good question. The fact that you even know that this is your problem, it's
Yeah.
it's good.
Yeah,
Usually the best indication of poor clustering or that's a when you see a lot of bitmap scans on indexes, you know that the database assumes that the column has very poor correlation, and you see instead of an index scan, you see an index bitmap scan. So that's usually a good indication that you should worry about correlation.
Mm-hmm.
Okay. Junior developers, man. Just not knocking. Okay. Anybody else want to say something? I appreciate any comments you might have on the presentation. If you found out about new types of indexes, maybe learn something new.
Yeah, this will definitely be a reference talk for me to visit in the future. Where I know there might be an index, and I usually Google DjangoCon talks and skim through the part where I remember something related. So that will definitely happen with this talk in the future.
I'm glad I could help, man. That's great news. Thank you. So anybody else want to say something before we pack up and move on to the chat? Okay.
Hello.
Thank you all very much. It was great being here.
Thank you. It was a great talk.
Thank you all for viewing. Thank you. Bye.